is a basic thermodynamics. Sorry. Hello, please mute your audio.
Sir.
Yes.
Sir, it's still the same thing. Can't display content. There was a problem in displaying the content.
Prerna, I think I cannot help you. You just go here to my audio. We'll sort it out later because others are not facing. Only you are facing this problem. So I don't know what exactly the issue at your end.
That's
right now. I may not be able to help you. Okay. Did you face similar problem yesterday?
No, sir. No, sir.
Huh?
No.
Okay. Stop discussion. Mute your brain. My suggestion to you is you just wait. Let this class be over because right now I'm not in a position to help you. Let's see. Okay. You can just listen to audio. Later you can watch video. Okay. That is the best I can help you. Okay. So all of you, please switch off your audio. Please switch off your microphone. All of you, please switch off microphone. Right. Okay. So this is the subject basic thermodynamics. Subject code is 18ME33. Contact hours 4 hours per week. So it's a 3 credit course. There will be as usual 40 marks for internal evaluation, that is continuous internal evaluation, and 60 marks for the semester university examination. University examination will be, question paper will be for 100 marks, and then it will be reduced to 60 marks. You have to write 3 assignments in this subject. Okay. So my name is Dr. Shankar Gowda, Nammandavar. Okay, I'll be handling this subject, and your next semester, similar continuation of the subject is applied thermodynamics. That also I will be teaching you. So this semester I'll be teaching you basic thermodynamics. Okay, this is the first course. Then that in thermodynamics, basic thermodynamics. Then later it is applied thermodynamics. Okay, so let's go to next slide. So what are the course outcomes? The course outcomes are explain the fundamentals of thermodynamics and evaluate energy interaction across the boundary of a thermodynamic system. Okay. Then next I'll just run through this, read them, then I'll explain what they are. Okay. Evaluate the feasibility of cyclic and non-cyclic processes using second law of thermodynamics. Apply the knowledge of entropy, reversibility, irreversibility to solve numerical problems, and apply first law of thermodynamics to closed and open systems, and determine quantity of energy transfer and changes in property. Interpret the behavior of pure substance and its application in practical problems. Recognize the difference between the real gases and ideal gases, and evaluate thermodynamic properties of ideal and real gas mixtures using various relations. Right. So some of these technical words may be new to you. At least some of them you might have heard already. Right. I'm sure all of you have heard the word thermodynamics. Okay. Most of you might have heard the word thermodynamics. It may not be very new to you. At least in chemistry or physics, this term might have been introduced to you. Okay, so these are the course outcomes. Let's not worry about them. Many other items listed here might be new to you. You may not right away may not understand them. Okay, so these are 5 objectives, 5 outcomes that we expect when you finish this course. Okay, so let's go to topics that we will cover in this. So what are the topics we'll be covering? Something wrong with this? It's not moving. Okay, it's not working. Anyway, So there are totally 5 modules are there in this subject. So the first module is about the fundamentals of thermodynamics. Then there is in the thermodynamics there is something called microscopic view and macroscopic view. How we approach the problem. Basically, thermodynamics is the study of energy, right? Energy, and it's where what happens when there is an energy interaction with the material. When material is if you have a material, to the material if you supply energy, what happens? So all that study is known as a thermodynamics. So there is something wrong. Just bear with me. My computer. One minute, please.
Yes.
There is something wrong. It's not going further. Just hang on. Yeah, okay. So what are the learning objective of now? Am I audible to you?
Yes, sir.
Okay, okay, fine. Sorry,
Yes, sir.
there was some disturbance. So course learning objectives. What are the learning objectives? Learn about thermodynamic system and its equilibrium. Okay, what is equilibrium and all we'll see later. Don't worry about that. Understand various forms of energy, heat transfer, and work transfer. Right. Then study the basic laws of thermodynamics, including zeroth law, first law, and second law. Interpret the behavior of pure substance and its applications in practical problems. Study the ideal and real gases and evaluation of thermodynamic properties. Topics in this course are fundamental concepts and definitions. That is the first module. It is thermodynamic equilibrium. This is also included in first module. Zeroth law of thermodynamics also comes under first module. Work and heat is in the module 2. First law of thermodynamics is included in module 2. Second law of thermodynamics comes under module 3. Entropy is module 3. Availability, reversibility, general thermodynamic relations is included in module 4. Pure substances is module 4. Ideal gases and the real gases, that comes under module 5. So this is how your syllabus is structured. These are the topics we'll be discussing in this semester, right? So course outcomes, I think I went through it already. So these are the course outcomes. At the end of course, you should be able to do all these things what are listed here, right? Okay. So some of the words, some of the things that are cited here might be very new to you. Then you might not have come across. But certain things like thermodynamics, you know it already, right? First law of thermodynamics, you know. Second law of thermodynamics, you know, right? Let's go. So scheme of evaluation, as far as scheme of evaluation is concerned, you know that the semester end examination will be set for the 100 marks and obtained from the marks obtained from 100 marks will be reduced to 60 marks. In video semester end exam, there will be 2 questions from each module. The students will have to answer one full question from each module. That is same that what you have done in first year. Okay, same thing will continue here also. So internal, as far as internal evaluation, there will be 3 tests. Each test will be valued for 30 marks. Please switch off your microphone. Avinash. Okay. So, and there will be assignments, 3 assignments you have to write, and maybe quiz we'll have in class, and then there will be attendance will carry certain marks. Okay, and there will be a class test. Okay, so that all that put together will carry 10 marks. 40 marks will be for the test, 3 tests, average will be taken. So 30 marks will be for test, 10 marks for the assignment, quiz, and a class test. So together internal evaluation will be for 40 marks. Okay. So most of these things you know it, just for your reference I'm putting it here. So let's go to the module 1. Module 1 will be studying first of all the fundamental concepts and the definitions, thermodynamic definition, scope, macroscopic and microscopic view, thermodynamic properties, thermodynamic state, thermodynamic equilibrium, zeroth law of thermodynamics, and then concept of temperature or definition of temperature will discuss in this first module. These are the topics we'll be discussing in the first module. Let's go to the fundamentals, the basics of thermodynamics. What is thermodynamics? So thermodynamics is the science of energy transfer and its effect on physical properties of substances. Okay. So what happens? All of you understand energy, right? So what happens when you add energy to the material? You add energy or remove energy. Okay? Energy is in different forms. Energy can be in the form of work or in the form of heat. Suppose you add heat, in the form, energy is added in the form of heat. So all of you know, if you heat some material, what happens? Its temperature increases, right? So similarly, if you add work, suppose you work, right? All of you have a common example. You rub your hand, right? So what happens? You feel warm feeling, right? So if you add work, then also the temperature increases. So basically, thermodynamics is energy transfer and its effects on the properties of a substance. Okay, it is based upon observation of common experiences which have been formulated into thermodynamics. So basically, thermodynamics has evolved by observing day-to-day activities. Okay, so what happens if you heat water? It becomes warm and then hot and then it becomes steam, right? Suppose if you have a closed container, let's say pressure cooker, right? If you have open vessel, water will evaporate, boil, and then evaporate. Suppose you have a pressure cooker kind of thing, pressure will increase than atmospheric pressure, right? When pressure increases in too much, then what a whistle blows, right? So these are all the changes that happen. So these are something that we observe in our day-to-day life. So based on these observations, okay, people have given a lot of thinking on that, why it happens, how it happens, right? So looking at this common observation, what you see around you, right? That observations, what you see around, closely observe, and then people have formulated into thermodynamic laws. Okay, there are important laws which govern the working of the universe. Okay, anything, everything on Earth, not Earth, in the universe follows these thermodynamic laws. Okay, now these thermodynamic laws have been taken to be as a laws of nature. Earlier when they were formulated for the thermodynamic applications or mechanical applications, engines and all. When people were studying energy engines, that time these laws were formulated. But later people found that these laws are equally applicable across all the disciplines, not just mechanical engineering. Every branch of science, these laws are applicable. They hold good in everywhere. So therefore, now they have been treated as a laws of nature. Okay. So let's go. So these laws govern the principle of energy transfer technology, notably in. So these laws are applicable in so many fields. I have listed so many fields here. This is not exhaustive list. This list is endless. Just to give you an idea. So these are all the technologies or areas where these laws govern the energy transfer. So start with the nuclear and steam power plants, internal combustion engines, gas turbines, air conditioning, refrigeration, gas dynamics, jet propulsion, compressor, chemical processes in plants, direct energy conversion devices. So all in all this is not end. Okay, you can go on listing, right? So many technologies, in many such technologies, laws of thermodynamics are applicable. Okay, so one must have a sound knowledge of the thermodynamic laws before trying to understand or work with these technologies. Or you want to, let us say, you want to develop, improve the existing technology. Let's say tomorrow you join some thermal power plant. So day-to-day working of the thermal plant, as well as let us say you try to improve. So you feel that I need to improve this thermal power plant. Then one must have a sound knowledge of thermodynamics, all three laws: Zeroth law, first law, and second law of thermodynamics. Without proper understanding of these laws, one should not try to do anything with these technologies. If you don't understand these laws, then don't do it. Okay, because they are governed by these laws. Okay, a sound understanding of the thermodynamic laws is very, very important. Right? If you don't understand these laws, then no point in working with these technologies. Okay. So just to start with the internal combustion engine. What is internal combustion engine? All of you know this, right? IC engine. IC engine, what it does? Can you imagine life without IC engine? No, not possible, right? You just look around. Everywhere it is IC engine is there. The bike you ride, the bus you travel, the car you drive, right? The train you go in, or anything. Just any automobile sector is full of IC engines. IC engines, what they do? Basically, IC engine converts one form of energy into another form of energy. What is the form of energy it converts into? It converts the chemical energy that is there in the fuel, fossil fuels, it's petroleum or a diesel, petroleum products like gasoline, diesel. They have some energy stored in that. That energy is converted. How it is converted? First, it is there is a chemical reaction. The petroleum product burns. Basically, it's oxidation. The petrol is oxidized. Burning is nothing but oxidation. So when you put this petrol in the IC engine chamber, it burns. It gets basically oxidized. When it gets oxidized, lot of energy is released. During that oxidation reaction is an exothermic reaction. Huge amount of energy is released. An exothermic reaction means enthalpy of a product is less than enthalpy of the reactants. So what you get? You get a energy liberated. The difference in energy comes up as a heat. So that energy causes rise in temperature. Rise in temperature causes a rise in pressure. So this increase in pressure acts on the piston, right? Piston is connected to connecting rod. Connecting rod is again connected to the crank, right? So when the pressure acts on the piston, it drives the crank. Crank is mounted on a shaft. Okay, it rotates the shaft. The shaft is coupled to a gearbox to your wheels. Then the wheels are driven, right? So that is how the energy that is stored in the petrol is converted into kinetic energy of the vehicle. Okay, this kinetic energy we use for transportation. We move things from one place to other place. We travel from one place to other place, right? Using this IC engine technology. This is basically conversion of one form of energy to other form of energy. This has a very important role in our day-to-day life. We cannot imagine our life without IC engines, right? Like that, similarly, other technologies are also equally important. The steam turbines or the nuclear steam or nuclear power plants. They are very important to us. The electricity that we get, right, every day, day-to-day use, the fan that you are using, or a fridge to operate the fridge inside, or AC, or the mixer. Morning, your mother will prepare chutney for you, right? You will not get chutney without the mixer. Mixer will not operate without a electrical power. Electrical power comes from either a steam power plant or a nuclear power plant. So without these power plants, our life will become pathetic, right? We can't imagine our life without these technologies. So similarly, the gas turbines. Gas turbines have a very important application. The aeroplanes have a gas turbine. Aviation sector is dependent on a gas turbines. Not only aviation sector, there are stationary power plants. Many stationary power plants are there which operate on a gas turbine technology. Okay, they use naphtha or a natural gas to produce electricity. Then air conditioning, comfortable living, human comfort, right, come from a air conditioning technology, right? Then refrigeration to store the food, right? Gas dynamics, like that. There are many things: jet propulsion, compressor, all these things affect our day-to-day life, and all these technologies are governed by the laws of thermodynamics. Okay, so let's go to next. There is two different approaches for the thermodynamics. One is known as a microscopic or a classical thermodynamics. Okay, with the relationships between the classical thermodynamics is concerns with the relationship between bulk properties of matter. Okay, what are the bulk properties? What are the bulk properties? Pressure, temperature, right? Volume. These are all the bulk properties which you can measure, right? Nothing is examined at an atomic or molecular level. So what we do is, suppose I add some amount of energy, or if I remove some amount of energy, what happens to its pressure? What happens to its volume? What happens to its the temperature? These are the properties. This pressure, temperature, volume we can measure. There are measuring equipments are there. We can measure these properties, right? So I can also measure the amount of energy added, heat is added or work is added. When I add this heat or work in the so what are the changes that happen? That we measure experimentally. Try to understand the behavior, correlation between energy and the properties. So here we are not interested in knowing what happens at an atomic level, because all this macroscopic approach was developed long back when people did not know that you know that in physics you have studied already that we earlier people did not know that material is consisting of atoms, molecules, right? Olden days people thought it is just mass, right? Full continuous, right? That is known as a continuum theory. When matter is continuous, people olden days they thought that matter is continuous. Any material if you take, because to a bare eye it appears continuous, right? But if you look microscopically through advanced technologies, X-ray diffraction, SEM, right, TEM, then you find that it is not a continuous, matter is not continuous, instead it is a discontinuous. Okay, matter is a discontinuous. So further, when the people divided and saw matter consists of basically matter can be divided into a smallest unit that is known as an atom, right? So these atoms are there are some 117 types of atoms are there in the universe, right? These atoms combine to form molecules, right? So that is because this macroscopic approach was developed before understanding that matter is discontinuous. Therefore, it was people never bothered about the molecular level interactions. They just thought about the change in pressure, temperature, volume, macroscopic property changes when energy interactions happen. So they were not worried about what happens because they didn't know that matter is consisting of atoms and molecules. Olden days people did not know. The laws of thermodynamics were developed much before the atomic theory of matter was understood. Okay? So olden days people did not know that, so therefore they never bothered about it. So they never bothered to correlate things in that fashion, right? Oh, can you hear me?
Yes, sir.
Am I audible to you?
Yes, sir. Yes.
Yes, sir.
Screen is problem. Screen is visible to you?
Yes, sir.
Yes, sir.
Okay, fine.
Yes, sir.
There is something is going on. I don't know what is happening. Okay. So then another approach of thermodynamics is known as a microscopic view. So what happened is we know that people developed this first law, zeroth law, second law. That was fine. They understood. It was well understood and proved beyond any doubt that these laws have to be followed. But later it was people when the later investigations found that matter is consisting of the atoms and the molecules. then people try to look at atomic levels how things happen. So they were able to come to same conclusion. Whatever macroscopic approach was giving the understanding, same understanding they were able to arrive at by looking at a microscopically, or this is also known as statistical thermodynamics. The famous example for the statistical thermodynamics is kinetic theory of gases. All of you have studied kinetic theory of gases. Everyone knows about kinetic theory of gases. Can anyone respond? Yeah, Durga. Yes, Rakesh. Have you heard of kinetic theory of gases? No. No. Anyone is there? Yes, Vignesh, come on. All of you heard, right? Yes or no?
Yes, sir.
Right?
Yes,
So
sir.
in kinetic theory, what you do? You take a gas particle, right? Apply the laws of mechanics, right? Momentum transfer, energy transfer. Then you come to a equation for pressure, right? Yes or no? Kinetic energy of a bulk kinetic energy is related to the temperature. You derive that equation, right? So that is known as a microscopic approach or a statistical thermodynamics. Okay. The macroscopic approach is your usual Boyle's law, Charles law. They give relation between pressure, temperature, pressure, volume, right? So there it is just experimentally measure the pressure and the volume, keep other property constant and check how they are related, right? So that is a macroscopic approach. Kinetic theory of gases is known as a microscopic approach. Okay, so this is how the thermodynamics evolved, and people found that both microscopic and macroscopic approaches converge. They point to the same thing, right? There is no dispute between them, right? They don't disagree on anything. They arrive at a same result. It's like something like, whether you go to Mangalore by on national highway or you take some other via route, say from here, let us say you go to Vitla, then from university, then go to Mangalore. At the end, you reach Mangalore only, right? Like that, whether it is macroscopic approach or the microscopic approach, they give the same result at the end. Okay, so therefore both are considered. Both approaches are used depending on the context. Whether a microscopic is proper for you or a macroscopic is proper for you, one has to decide. Suppose if I'm looking at a reaction kinetics, then one has to go for the microscopic view, the reaction thermodynamics, right? Then one must have knowledge of a microscopic approach. If you are not looking at just a pressure temperature relation, you want to study, so then it is not necessary to know what happens at microscopic level. Just the microscopic relation between a temperature, pressure, and a volume is sufficient for you. The real gas equation, famous real gas equation. If you have a sound understanding of that, that is fine for you. Okay, so that is how both macroscopic and the microscopic approaches are used in thermodynamic study. To move forward, unfortunately, my slide is not moving. Just give me a minute. Let me play with. Let's see what I can do with this. Okay. Nitin has come. Nitin is there. Nitin is absent today. Oh, sorry, not Nitin. Akhilesh is there. Akhilesh has come. Okay, fine. Ashik. Ashik, are you there? Ashik, can you hear me? No? Shailesh? Sorry. Ashlesh. Ashlesh is there? Ashlesh, can you hear me? Chirag? Dikshit? Dikshit, can you hear me? Okay, it's working now.
Hello,
Yeah, Dikshit is there?
Rakilesh sir. Miss.
Akhilesh is there?
Yes, sir.
Who is this?
Rakilesh sir.
Akhilesh, okay, fine. Dikshit is there? Ashik is there?
No.
No? It's okay, fine. My slides have come back. We'll discuss this. Huh? There's some problem with this, man. Slides are not. You are able to see the slides, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So, as I said, there is a macroscopic approach and a microscopic approach.
Macroscopic.
Both are valid. Both give you same result. So, as I said, there is a kinetic theory of gases you have studied in PUC. What you do is you consider this gas as a small particle of mass, some mass m, then try to apply the laws of mechanics to this, then statistically sum it up to arrive at a bulk behavior of the material, right? So this is how we try to get the behavior of the material, thermodynamic properties of material, by looking at the interactions at the microscopic level. So then it is called a microscopic approach for thermodynamics. Then macroscopic is just study the properties and try to find out, figure out the interaction between energy and material. That is a macroscopic. As I said, Charles' law and Boyle's law, they are example of the macroscopic approach, right? So that is how this is how the thermodynamic subject evolved, and the laws were codified, and they were proven that these laws have to be adhered to whenever you do anything that happens on Earth, in the universe. He follows this laws. Nothing goes against this law. If somebody says tomorrow, somebody says that first law of thermodynamics is not valid, right? First law of thermodynamics is nothing but a conservation of energy. If somebody says energy is not conserved, I can generate energy from zero, then the whole thing will collapse. Entire our scientific and technological understanding will have to be changed, because so as on date, these laws hold good. Nobody has proved them wrong, right? So,
Is it possible, sir?
sorry?
Is it possible to prove it wrong?
I can say almost impossible. Okay, almost near to impossible, right?
Okay.
But nobody knows. Tomorrow somebody may, because science is always open to questioning, right? So as on date, it's fine, but you just don't make stupid argument. If you have a sound understanding and try to do it, that's fine. Because as you know, just to give you an example, olden days, if you see people believed that the sun is going around, right? Sun rises and the sun sets, right? Sun rises from east, sun sets in the west. This was based on observation, nothing wrong in that, right? Olden days, people did not have means to see or visualize how things are happening in universe. So that was fine, right? So based on that, they evolved their own concepts, right? Their own, like all this, calendar, panchanga, all those things were based on these observations. But they were built on some wrong fundamental, right? So then you have to throw it. When people realize that the sun is not moving, instead Earth is going around the the sun. So you have to discard all those understanding. There was volumes of literature which is available in our olden literature, which says that, but we have discarded it. Like that, it might or might not happen. If it is proved, then believe me, every book of engineering and science what is written is available today. We have to throw them to dustbin and once again write new books. Okay. So to that extent, it is impossible. I can say. I don't say totally it is impossible. Near to impossible, I can say. Okay. Hope I have answered your question. Are you happy, Prerna?
Yes, sir.
Can you hear me?
Yeah.
It is almost impossible. You can take it from right now.
Okay, sir.
But we don't know. Future, nobody knows. Okay.
Okay, sir.
So unfortunately, my slides are not. There's something wrong with this. Okay, I think we're running out of time. We'll close this. If there are any questions, I'll be happy to answer. Prerna had some question. Anyone has any doubt? Please raise your doubts. I'll be happy to answer. Anyone else? Prashant? You have any doubt?
No, sir.
No? Puneet? Unfortunately, my slides are not uploading. Something wrong. This is hanging. I don't know what is wrong with this.
So should we write it down, whatever you said?
Sorry?
Or will you be giving notes?
I'll give
Will
notes.
you be
Don't
giving
worry.
notes?
No, don't write. No writing business. I'll give notes. Don't worry.
Okay,
Don't
sir.
write. Not possible for you to write. Just listen to me.
Okay.
During class, don't try to write anything. Okay.
Okay, sir.
Even this video will be available. You can see this video later. In this team software, you can see this video later. So don't try to write anything. Don't waste your time. Concentrate, because first thing is you are not able to hear properly, see things properly on screen. That itself is difficult. So over that, don't take up another task of writing. Don't do that. You'll get the notes, everything you'll get. Don't worry. Yeah, it's coming. Can you see the slides now?
Yes, sir.
Okay. Now it's coming up.
Yes, sir.
Okay, fine. So one more slide I'll take up and then I'll close. We'll close the session. So as I said, there is a macroscopic and microscopic approach. Both are valid. Okay. So just a small definitions. Let us take. Often I'll use these terms. So system, boundary, and surrounding. Okay. These terms will go on using every now and then in thermodynamics. So what is a system? A quantity of matter or a region in space chosen for study. What is system? I take some space, I consider this is my domain of study. I define, right? So that is called system. If I define something and say I want to study energy interaction, for example, there's a fridge, right? In the fridge, you want to do a energy interaction study, energy budgeting. So then fridge becomes your system. Or let us say air conditioned room is there. You want to do energy interaction study of a air conditioned room. Then your air conditioned room becomes a system. Or let us say you want to do the energy study on some large, let us say Earth, right? You want to do energy study of Earth. Let's say what is the amount of energy received by Earth from Sun. Radiation energy falls on Sun, right? So Earth gets radiation energy from Sun, and also Earth radiates energy. Sorry. Yeah, please mute your microphone. So our Earth also emits electromagnetic radiations, right? So our Earth loses energy and also gains energy. You want to do some budgeting of this. So then your entire Earth atmosphere becomes your system. So like that, system can be anything. System is a matter or a space in region in space chosen for study. Surroundings is the mass or region outside the system. I define something, then everything else is called a surrounding. Okay. Boundary is that something that separates the system and the surrounding. It's called a boundary. This boundary can be real or imaginary. It may not be a real boundary. Suppose you have a balloon, you blow air in the balloon, right? So then balloon surface becomes a boundary. Inside air is the system. I want to do some energy study, pressure study, right, like that. So then the air inside the balloon is my system. Surrounding air is the atmospheric air is the surrounding. The balloon becomes a boundary between the air and the surrounding, like that. So this is a boundary can be imaginary or the real. Okay, both are possible. So these terms, just rehearse them, go through any book. So system, boundary, and surrounding should be, you should be thorough with the definition of these things. With this, I think we'll close today's session. Thank you very much for all of you. If you have any doubt, please raise your doubts. I will answer those doubts, and then we'll wind up. Anyone has got any doubt? Yes. Yes.
Yes.
Okay. If there are no doubts, we'll wind up the session. Shashank, you have got any doubt? Fine, then
No, sir, no.
close this session. These people did not respond. If they are there, just they can say yes. Ashik, Ashlesh, Chirag, Arpit Rai. Arpit is there? Arpit has come? Then I'll mark absent for them. Okay. Hitin Rai is there? Prajwal K. Prajwal K is there? No. Pramod
Sir.
K.
Yes, sir. Arpit is talking.
Pramod is there?
Yes, sir. Yes, sir.
Pramod is there?
Yes, sir.
Pramod? Yeah, Pramod is there. Okay, fine. Pramod is there?
Yes.
Then Shamant. Shamant is there? Ranjit? Ranjit is there? No? Shamant is not there. Ranjit is not there. Shashank? Okay.
Yes, sir.
Shivprasad? Shivprasad? Sujan Alva? Okay, all these people I will mark absent. Okay? Fine.
Hello.
Okay, all the best.
Yes, sir.
Bye-bye. You can leave me now. Shall I close this?
Yes, sir.
Okay, bye. Bye-bye.
Yes, sir. Bye bye. Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Yes, Krishna.
Manvite.
Pramod.
ಆಯ್ತಣ್ಣ ಮದ್ನಣ್ಣ
ಆಯ್ತಣ್ಣ ಮದಿನ್ನಂತ ಹೆಚ್ಚಿನ ಕಥೆ
ಬಾಯ್
Gappa chuppu. There